So hello guys, my name is Shivam Pandey and you are watching on Discover and Uncover YouTube channel. And in yesterday's lecture, we have covered that what is a tree and what are the basic terminologies used in the tree. And we have also discussed the various types of trees. Now we are having a new topic for today, that is types of trees. Now we will discover and learn about the different types of tree that we have in the data structures. So beginning with, we have the different type of trees name, like a general tree, binary search tree, avian tree, red black tree, and an array tree. Okay. So let us begin with our very first type of tree, which is the binary tree. So binary tree is a special tree data structure in which each node can have at most two children. Yeah, so it is very much clear by the definition only that it is a type of data structure in which each node can have at most two children. We have seen in the previous lecture that a tree can have as many children as it wants. There are no fixed rules for this. Yeah. Now we have made some uh, foundations or limitations that a node can have only two children. That means a parent can have only two children. So here we can see in this diagram that each node is having at most two children only. We see A, it has children of B and C. B has D and E. C has F. Now if a situation occurs where B is having children D, E, and let's suppose J, so that would be a case that B would be having three children. So that case is not uh, the case which satisfies the condition of binary tree, and this example would not be a binary. Then it would be different type of tree. I would say that it would be a normal or an ordinary tree, but not a binary tree. Yeah. So it is quite obvious that was binary tree. Now let us discover a second type of tree, which is unlabeled binary tree. Yeah. So unlabeled binary tree means that in the node there is nothing printed over it, and we have no labelings on the node. For example, in this diagram, you can see that there is no naming on the node. The nodes are put blank and they are just blank. So we have been given a formula here. Number of different binary trees possible with n number of unlabeled nodes is equal to 2 NCN upon n plus 1. So I hope you all know that what is NCN, and you all know about the formula of how to calculate NCN. Yeah, right. So for 2 NCN, let me just quickly tell you that how to calculate this 2 NCN. So for calculating it, we have to write 2 NCN equal to 2n 2n factorial, factorial. This is factorial sign. Sorry, and divided by n factorial in brackets multiply by 2n minus n factorial. 2n minus n factorial, which means if we simplify it, then it becomes n factorial into n factorial. Yeah. So if you solve it on simplification, then 2n factorial will become 2n factorial, and n factorial will be cut out, and this would be 2 upon n factorial, and below it you have n plus 1. You can also solve it like this: 2n factorial and n plus 1. So yeah, by this method also you can solve it, but I would say that this is not the correct method, because and this formula is also very much easy to just remember and solve, right? So if you remember this formula that is written over here, it would be easier for you to solve. So just look upon this formula and remember it for any future response or any objective question that you might face in your future exam. Yeah, so also an example is given here. Consider we want to draw the quantity, all the binary tree possible for an unlabeled tree of three nodes. Yeah, so it is a unlabeled binary tree which is having three nodes. which are not labeled and which has no labeling on it. So by the formula, we have formula 2ncn upon n factorial. One, sorry, n plus 1 factorial. Sorry, n plus 1 only. Sorry. N plus 1 only. Yeah, so for this, we have 2n. So the value of n is 3. So it will be 6cn, which is 3, divided by 3 plus 1, which is 4. So the value of 63 would be 6 factorial, or we can say 6 into 5 into 4 factorial divided by 4, into 3 factorial by 3 factorial by by 3 factorial into 2 factorial, which is 6 by 6 minus 4. So it would be 3, 3 factorial will cancel, 2 and this 2 gets divided and it's then by 2. So it would be 6 into 5, 13 to 260 divided by n plus 1, which is 4, and by 3 also. So 3 will be remaining. So 15 by 3, which gives an answer of 15. Yeah. So, sorry, 5. So the answer is 5 for this. So there are 5 possible ways or 5 possible diagrams that we can mean by and we can make by this 3 nodes which are unlabeled. Like you can see from this figure also, that the first one is unlabeled diagram and it is having 3 nodes. So this is the first thing or first type of diagram that you can figure that you can draw from 3 unlabeled nodes. Second one is this one. Third one is this one. Fourth one as this, and so it is only the permutation combination to make the nodes and make these diagrams. This is not something that is very mathematical or something, but it is quite like permutation combination, basic permutation combination, and just making out figures out of something. Yeah, so now let us learn the labeled binary tree. So it is the clear by definition itself that labeled binary tree will have label or any number or any letter or any alphabet printed over the nodes. Yeah, so you have seen it, and I don't need to waste my time upon it. And the formula for calculating out the number of possible trees from n labeled tree nodes are 2ncn divided by n plus 1 into n factorial. So the previous formula was 2ncn upon n plus 1 only. But now here we see that the formula becomes 2ncn upon n plus 1 into n factorial. So we have to multiply the whole result by n factorial. So why is it so? Uh, I can explain you that also. Uh, let's suppose, okay, so here we have given three label nodes, and firstly, if you have this confusion that why it is so that we are multiplying by n factorial in some times and why we are not in some cases, then you take one thing, then you take a node of or diagram or a tree of three nodes, correct? And then you try and make the possible results out of these three nodes, that what figures can you make from this node. Yeah, so when we try to make this, uh, sorry, here numbering is not given here or alphabets are not printed over here, but it would be A, B, and C. I'm just correcting this thing and I'm writing on the note. Yeah, so A, B, and C. And when we print it over here, then we see 6 different diagrams. But in the diagram, what we see is that the number of possible binary trees here possible is 30. So here are 30 possible ways by which we can draw this. Yeah, so 30, the drawing 30 uh, trees is a very much, I think so, boring task. And you know that the basic logic behind it, and you can also try and test it at your home. by drawing all these 30 figures, and you can see that how small changes and small just geometric things changes the whole tree structure and the whole properties of the tree. Also, I'm just suggesting you that if you get time, then do calculate the degree of these these five trees. Do calculate the degree of every node, the height of every node, and the yeah, just only two things: height and degree of every node. You calculate it and keep it and keep it with you only because it is for your benefit only. Yeah, coming towards a full and a strictly binary tree. So a binary tree in which every node has either zero or two children is called a full or a binary tree. So here there is a strict guideline that every node should have only zero or two children is called a full binary tree. Yeah, so strictly means that if a parent is having one child, then that won't be considered as a full binary tree, and that would not be the case here. So you have to just strictly check that every node has two children. Yeah, so in this case, you see that C has only one children. So this is not the case of binary tree that we can see from the figure itself. And in this figure, we see that he is having no children. That is acceptable. A parent can have zero child, and that is totally fine. And yeah, so that's the completely sorry, fully binary tree. Now let us come upon complete or a perfect binary tree. So a complete binary tree is a binary tree that satisfies the following two properties. So now what are the properties that a complete binary tree follows? So the first property is that every internal node has exactly two children. All the leaf nodes are at the same level. Correct? So every internal node has exactly two children mean that internal node like B and C are the internal nodes, but C is having no children. So every internal node should have exactly two children. If internal node has zero children, that would not be considered because it was considered in the previous case full or a strictly binary tree, but it won't be considered here. So a node has to have two children to make it a like complete binary tree. Yeah. So from the example also you can see that uh, C is having two children here, F and G, so it would be a complete binary tree. Now come towards almost complete binary tree. An almost complete binary tree is a binary tree that satisfies the following two properties. All the levels are completely filled except possibly the last level. The last level must be strictly filled from left to right. Yeah, so the two properties are the first property is I am trying to explain you is that all the levels are completely filled except possibly the last level. Yeah, so now let us see that all the levels are fully filled or not in the first case, in the first diagram. Yeah, so A, B, C is filled, D, N is filled, C is having one child F. So I don't think that uh, no, there is any issue here. But if we consider the second point, the last wire must be strictly filled from the left to right. Yeah, so this is the problem which we are facing here. So last level would be must be filled from left to right. But here in the first figure we see that F is associated with the right side of the like this last node. So we have to have it on the left side of the node first, and then we can have it on the right side. That would be a conventional way for this. Yeah, so now let us come towards tree traversal. In order to perform any operation on a tree, you need to reach to the specific node. The tree traversal algorithm helps in visiting a required node in the tree. So now let us see that what it is written in here. In order to perform any operation on a tree, you need to reach to the specific node. The tree traversal algorithm helps in visiting a required node in the tree. Tree traversal refers to the process of visiting each node in a tree data structure exactly once. So a tree traversal is nothing but moving from one node of a tree to the another. Now you might think that what does moving from one node to another means. So, for example, if you are on a root node of a tree, and you have to reach the bottommost or the bottommost layer or the nth height of the tree, then what you can then what you can do that you can traverse the tree and you can reach to that node. Correct. So the tree traversal techniques are given here. We have two types of tree traversal. Basically, the main two types are there, which are DFS and BFS. So DFS depth first traversal and BFS is the breadth first traversal. So depth first traversal is consisting of three different types of traversals: pre-order, in-order, and post-order. Now people get confused in these things, that what is pre and what is post and in order. So it is very basic and very much like quite easy thing if you get the concept very easily very soon. So in the pre-order, let me be very clear about the type of nodes first. So the type of node I know that I have taught you is parent node and the child nodes. For child nodes, we have been seeing that having two types of child, the left child and the right child. So, for example, if we have having a left child, then we can name it, for instance, here L, and the right child we can name it as R, for instance only. Okay. So it would make a like abbreviation of P, L, and R. P, L, and R. P denotes the parent, L denotes the left child, and R denotes the right child of the and R denotes the right child of the parent. Correct. So now let us see what is pre-order traversal. Pre-order traversal is when we have the parent in the first place, then we have left and the right subtree. Yeah. So PLR is the, you can say, the basic formula that we have to follow in the pre-order traversal. So let us see here what is the pre-order traversal. For this pre-order, we have to see that the root node comes at the first place, then the left and the right cell. So this is the question, sample question given here. So let us try and solve the pre-order traversal. Pre-order. So now we are at a place of A, which is a root node. So let us now. So it is a parent node also. So now we can name it as pre-order as A is the parent. Yeah. So now let us take the left side, or sorry, the right side of the right subside of the root node, which is B. So B here, and in pre-order, we have parent as the, so B is the parent here. So it is the parent. Now we have to find L and R for B. So for B, the L and R are B and E. Sorry. Yeah, E. E. B D N A. So it is L and it is R. P, L, and R. As you can see, A, B, D, and E. A, B, D, and E, which I have made, and upon completing this, then we move towards the right side of the root node, C. So C, and then we have the left child and the right child as well. So after C, the left child is F, and the right child is G. Correct? So it is P, L, and R again. Yeah. So this was the pre-order traversal, and now we understand, and now we try to learn what is in-order traversal. So in in-order traversal, follow the sequence of L, P, and R. So what is now LP and R? So L denotes the left subtree, P parent, and R right subtree. So left, parent, and right, right. Yeah. So now let us see that what we can make from here. Uh, so the same diagram we have taken here also, where is the root node of this tree, and A uh, A, D, B, E, F, C, and G. So now let us see that so in order we have to take the parent node in the middle of the child. So here D is the left child, and B is the parent, E is the right child. So yeah, DB is the sequence for the in order, and A, as we can see that it is the root node. Always remember that in case of in order traversal, the root node always comes in between the the two subsides of the tree. So here we can see that A is between all the like this subside and this subside. So A is between those sides, and it is the parent node for this. So the sequence becomes GBE. Uh, then we have F, C, and G. D, B, E, A, F, C, G. So yeah. So it is a sequence that we can see here. Yeah. So now let us move towards post-order traversal. So the post-order traversal is a traversal where we follow the sequence of L, R, and P. So what is LRP? Again the same thing. L is the left subtree, R is the right, and P is the parent node. Correct. So for this diagram, let us try to find out the post order traversal. For the post order, let us see that what is the post order traversal for this tree. So for post order, we have D, E, uh, D, E, B, A, F, G, and C. F, G, C. Oh, sorry. It was my mistake. Uh, D, it is D, D, E, D, E, B. Up till it was correct, but the root node has to be at the last place of the tree. So it has to be D, E, B, F, F, G, C, A. Yeah. So you have to make this D, E, B, F, G, C, A. Yeah, so that's all for now for this lecture. And in the next lecture, we will like study what is a binary search tree and how to insert elements in a binary search tree, and what are the properties of binary search tree. Correct? So that's all for now. So thank you guys.